Welcome, everyone. Thanks for having joined this seminar, both in person and on Zoom. So we are continuing the series of Climes seminars related to climate hazards and climate impacts. And today we have a guest from Chalmers University of Technology in Gothenburg, Hans Chen. And Hans has conducted some work on atmospheric rivers over Scandinavia, which are a major source of precipitation-related climate hazards. And as usual, we'll have the seminar and then time for questions both from the in-person audience and the Zoom attendees. So please, Hans.
Thank you very much. And thank you so much for inviting us to come here. Very happy to visit the department and also to part in this Climes seminar series. So yes, as mentioned, I'm Hans, and we actually recently got a new department at Chalmers called the Department of Environmental and Energy Sciences. So we used to be called Space, Earth and Environment. Now Space moved to Physics, and I guess they want to focus more on environment. But since Chalmers might not be the most well-known university, maybe in terms of climate science, I want to just briefly introduce myself and my group a little bit. So I call my group the Climate Dynamics Group. And we need to take a new picture because this was from about 2 years ago at the Swedish Climate Symposium. Then we were only 3 people. Now we have expanded to double the size, and we have actually 2 members with us today. So one is Fang Yuan and one is Xin Yu, who are sitting in the audience. So they are going to work more on things related to climes, on this kind of impact and hazard, etc. So Fang Yuan, she's a PhD student. She wants to estimate or quantify the societal costs of, now we've decided to focus on landscape fires. So, and for now we decided also to focus on the health effects, but maybe in future we'll see where it goes. Could also be looking at calculating cost due to carbon emissions, for example. That's something I'm interested in, etc. And Xin Yu, she's looking at compound extreme heat extreme and pollution, focusing on Europe, and also seeing, for example, if you can look at the resilience to those kind of events and quantify that. So it's very interesting stuff. But the hero of today's talk is actually not us. It's Erik, who's in the circle here. He's my first PhD student, and he's the one who did most of the work that I'm presenting. He's actually going to present the same thing in 2 weeks for his midterm seminar. And the QR code is for our website, so I spent some time on that. So happy if you want to go and have a look afterwards. And well, atmospheric rivers, that's actually one of the topics I would say I've explored the least. So my background is in atmospheric science and climate science. I did my bachelor and master at MISU, Stockholm University. So we actually had some courses, one course, practical meteorology together, and also had this party together. Hope that tradition is still alive. So that was nice, but that was quite some time ago. And in my research, I started focusing mostly on the Arctic and also linkages between the Arctic and mid-latitudes. So that's quite a big deal a while ago about what happens in the Arctic, if that could impact the weather extremes, for example, that we experience. But actually we're actually even later than halfway through my PhD, we decided that I would switch topics to something completely different. And that would be looking at carbon fluxes over North America. Because there was one professor who got a big NASA grant, and they wanted to develop a modeling system for modeling those kind of fluxes and also using observations. So for this grant, we would fly airplanes and measure the concentration of the carbon dioxide in the air. And they wanted a system to be able to infer what the exchange was at the surface between, let's say, vegetation and the atmosphere. and also human emissions. And I wanted to, my advisor was an expert in something called data assimilation. It's a method to basically fuse information from different sources, for example, from models and observations. And I said I want to learn that. So he asked if I want to join this project, and I said, okay, sure, after some thinking. So that's how I then got involved with something quite different about with the carbon cycle. And now I'm actually looking at also human emissions. We're going to have some satellites, hopefully this year, the first one from Europe that are measuring carbon dioxide. So that's another side of my research now. Well, anyway, back to the topic of the presentation, atmospheric rivers. So people from Uppsala, I'm sure you have heard a lot about those already, since you had a PhD student working on this. But I'm still going to have a short introduction to atmospheric rivers. And yes, they are connected, as I said, to many extreme events related to precipitation. Did a quick search yesterday and saw that quite recent one that affected Spain and Portugal this year in early February. And so this was associated with the storm named Leonardo, and also then with an atmospheric river that led to flooding, and I think over 3,000 people got evacuated because of this. This was not the only one. It was actually a series of storms, and at least 2 of them also had atmospheric rivers embedded in them that led to heavy precipitation in this region. And as you know, when the soil gets sort of wet already, then if you have more rain, then it can't soak up the water, so then you get very easily these kind of floods. So that's one motivation to better understand atmospheric rivers. And this is a satellite image from Sentinel-3 showing, I actually don't know exactly because it didn't say, but I would guess this is the total water vapor in the atmosphere, because that's one thing Sentinel-3 can measure. So probably not clouds, I would guess. And you can see this long band here of the high water vapor is coming in and yes, hitting basically Spain and Portugal. And research has shown that ARs, atmospheric rivers, are associated with many extreme events such as floods. So this one said that 9 out of 10 major ones globally are associated with atmospheric rivers. And they are quite well studied in some regions in the world. For example, in North America, California as one example. So I pulled this from a weather discussion on the mailing list I'm subscribed to, where they looked at the forecast of a major atmospheric river event. So they actually use that in their forecasting. And what you see here is this is from a weather forecast model, and the arrows, it's basically water vapor transport. So it's a vector similar to wind. And the colors, that's just the magnitude of transport, similar to wind speed, but for the vapor transport. And you can see here, again, this kind of narrow and long structure. So that's why they're called atmospheric rivers. And this is using AR5 data that Eric made an animation. If you look at here over North America, you see it's quite common that you get this kind of atmospheric rivers making landfall there. So it's no surprise or no wonder that they're also interested in studying those. I know some groups now in, for example, East Asia, they're also increasingly doing research on atmospheric rivers. But if you look here on our side of the North Atlantic Ocean, you see that it's also quite many that are hitting us here in Scandinavia. This is in the winter. And then we started asking the question that, okay, so how many atmospheric rivers do we typically get in a year? Do we see any trends? How much of the precipitation is associated with atmospheric rivers and so on? So basically those questions for Scandinavia, their frequency, their precipitation, and also you saw that the seem to follow some pathways over. So can we find some typical pathways, and do we also see any shifts in those? And when we look at literature, we couldn't actually find the answer to those questions. So there have been some studies, but not so much focusing on just Scandinavia. So we said, okay, well, let's do just, we have the data. Why not just do a quick analysis of this? Quick and easy. Well, it turned out was not maybe so easy as usually is the case maybe when you do research. But we still got some interesting results that I want to share today. So the study region, Scandinavia, just for clarity, we define that as Sweden, Norway, and Denmark. And we also, so we use this now land mask, but we also expanded it a bit to smooth it to account for example, the coarse resolution of AR 5. That sometimes you can have an AR of land, but then in AR 5 maybe that's not land and vice versa. And also just sometimes we think that in AR that's maybe is close by, but not exactly making landfall, could still affect precipitation over land. The period 1982 to 2019, we would have liked more recent data, but the data set we used was only up to 2019. And this data set is called ARTMIP, stands for Atmospheric River Tracking Method Intercomparison Project. So basically, when you work with atmospheric rivers, you also need a method to track or detect them. And there are many different methods. And previous studies have found that if you use different methods, you can get quite different results. So this ARTMIP project, their aim is to sort of harmonize or have protocols for how to do this so that you can compare different methods, for example. So we chose what we call AR catalogs, so a bit from different methods, and we found 4 for this whole period that were global. So that's what we used. And then we also, for the associated precipitation, we used AR 5. And this we used both for the ARs and for precipitation. That was 6 hourly. They are hourly available, but previous studies mostly use 6 hourly, and it was also for computational efficiency. Okay, so I talked about this kind of different tracking methods. So just very simplified, how you think of it, is that you can start with the field of this water vapor transport I talked about. It's usually called IVT. I'll explain soon what that means exactly. But you can think of it as the transport of water vapor. So here's a snapshot in time for that. And most methods, they first apply a threshold on this in some way. For example, you can have just above some value, everything below that value is set to 0. So that's what you have here. So you get the more extreme values. Then you see that we still have a lot of like filaments, or whatever you want to call them, but maybe we are not so interested in, like a lot of small noise things. So those methods, they apply additional criteria. So for example, we often think ARs, they should be quite long. It shouldn't be like whirling around, because that's more associated with a cyclone. Maybe not those small things, etc. So you apply some constraints, so you filter out some of this, and you end up finally with your ARs. You notice also now I set them actually to the same, like there's no shading or no contours here. That's because in this ARTMIP dataset we used, they provide the data like this, basically like a mask where you have 0 where there's no AR and 1 where there are ARs. So that's the steps, but then in each step here you have different choices, right? What threshold to use, how to apply it, what kind of constraints do you want. And so those 4 methods we used, they were quite different. I'll get to soon. But first, this IVT, what is that? So this was, for me, actually an exercise to try to make an LLM model be able to explain IVT. And that turned out to be not so easy, so I tried to generate this. because I didn't have time to draw it myself. But finally, I ended up with something quite reasonable. But you see there's still some artifacts as expected from AI. So don't take this too literally, but just for our understanding, well, you have water vapor, often quite more closer to the surface, less up, higher up. And if some algorithms, they track ARs using just water vapor, for example, if you use satellites, but you have more water vapor in the tropics, for example, but you actually don't have much ARs in the tropics. And you maybe this close to ground, if it's not moving very much, then it's not really an AR. So most use then also the wind speed at different heights. And the wind speed, well, that's all like sort of opposite. You have low wind speeds close to the surface, and often it increases with height. And for example, you have a jet stream with propoles. But high up where you have jet stream, maybe that's quite dry. So maybe that's not so much water vapor transport. Versus here, the water vapor is not moving much. So often in the case, you have ARs sort of something in the middle of that. So here, that's where you have, if you multiply those two, taking into account like different densities and so on, you sort of get this water vapor transport. And this I then integrated, it's vertically integrated. So you just integrate this whole thing. So you get the photo. So that's basically what IVT means. And you can do this then for each grid cell. All right. So the ArtMap, I mentioned we used 4 different AR tracking methods. So here are the names of those. And actually just the first step with this thresholding, they all use different methods. So you have ones that use percentile based. So you get the percentile from climatology, basically. And that can also vary with season. So it varies with, you have one for each grid point. So it varies with location and with season. And the advantage of that is that from here in high latitudes, it's relatively dry if you compare to elsewhere in the world. But if you use this percentile based, then that takes account what the normal conditions are. And then if you're exceeding that, then you can say that maybe then you have an AR. This Munkenk, they actually, the result is a bit similar, but they do it differently. They remove the mean values for each grid point. And I think that mean is also vary with season. And then they have a fixed threshold on the anomalies. So it's quite somewhat comparable, I would say, to this first one Walliser. Tempest, they actually don't use the IVT field itself. They use the Laplacian, so the derivative of the derivative. And the reason for that is they want to focus sort of like on the ridges. And then finally, last one, maybe the simplest, is just a fixed, just a value. And this is actually quite high value. So we saw that this one misses a lot of ARs in high latitudes because of that. There's another variant which uses 250 instead, but that one was not available to us for this period, so we couldn't try it. All right. So here's just an example of what we did after we got, or Eric did, with this ArtMap data. So I mentioned that we got this on, it's a gridded, and it's just a 0 or 1, okay? And with our eyes, we can see that there are 1, 2, 3, 4, 5 ARs here, but it's not obvious if you just have this gridded data. So the first step is to separate those like blobs of ARs. And we just use a very simple imaging technique where you look at connected pixels, and if they're not connected, they are considered a different object. Second step is that this is for one time step. Let's say we look at the next time step, then all of those blobs will have moved a bit, right? And just for simplicity here, I just say that maybe this one moved here. I didn't draw all of them. I drew this because I didn't have the data. But let's assume it moved to this green one instead. There's actually nothing in the dataset itself that says that that AR object is the same as that, just moved. They are, yeah, there's no connection between them. So we needed to be able to track the ARs in time. We needed to link them in time. And the way Eric did it was that it's a quite simple index where it quantifies how much the objects overlap. So we look at the green one, and then we just search and see which other object overlaps the most with the green one. And then that's considered the previous iteration of that. Okay, so now we can follow each AR object in time. And finally, we just keep the ones that intersected with Scandinavia. So those in Pacific, for example, you can just throw them away. And if you want to be very specific or accurate, actually, we did the third step before second step, because second step is quite computationally heavy. You have many objects. I mean, relatively speaking, if you compare some things, it's not so much. But to make it a bit faster, we actually first selected the ones that intersect Scandinavia, and then only did this kind of time tracking for the ones that intersect them. Yes. So let's look at some results. Starting with this question, how often do they occur? This is their frequency and the average of the whole time period. And the max frequency are found around Denmark here, about 5.9% of the time during 1 year, which might not sound very much. I think that's equivalent to roughly 22 days. So in 1 year, you would have about 22 days of ARs in this region. Versus in other parts, it's a bit less. And you see this, it follows sort of the topography that seems like they are sort of blocked by the mountains here in Norway. Here in Sweden, some of the Sweden is more flat, so then the ARs can more easily penetrate into land. And then for the associated precipitation, the way we calculated that, in some studies, they just say, okay, we have an AR here. Then the precipitation that happens in the same place as the AR, that's the AR precipitation. We found that a bit limiting because maybe the tracking cuts off some of the AR, but the precipitation around it. Or it could be precipitation now going on and then the AR comes, but that's not the AR precipitation, right? So we did more a statistical approach. So it's basically like a composite in climate science. So we took all precipitation that occurs when we have an AR minus all precipitation occurs when we don't have AR in Scandinavia, for example. So this is the AR precipitation we get that when we subtract when we don't have ARs. And so you see that most of it is occurring along the mountains over Norway, not so surprising. This is basically where you have normally a lot of precipitation. So to be able to quantify this a bit better, here is instead the fraction in percentage of the AR precipitation to the total precipitation in a year. And then you can see that, okay, it can be quite high. It can be like over 40% of the precipitation in some regions here, especially over Norway, or can be associated with ARs. And you can see, for example, where we're from in Gothenburg, then yes, we also have some part of the precipitation associated with ARs, or in Uppsala, it's a bit less. Right. So this map, shows spatially right. But then if you ask over the whole of Scandinavia, how often do we get an AR somewhere of Scandinavia? And that's what this shows. This shows quite a lot of different things. So let me see. So the black line, that's the AR frequency anywhere in Scandinavia. So this is a bit higher, over 20%. So most of the time, because I don't care where it occurs, just if it's in Scandinavia somewhere, then I count like, yeah, that's an AR time step. The dashed lines, they are the range from, remember we had 4 different methods. So this analysis was done 4 times. And this is from the minimum to maximum. And you see that the range is quite large. And that's because the lower one, that was the last algorithm I mentioned, the 8500, which detected very much less AR than the other. And this one, the higher one, was one validator, which detected a lot of ARs. And this is the black one is the median value. But in general, if you look at, for example, inter-annual variability, they are quite similar. It's mostly the magnitudes that differ. Then the bars, that's the precipitation. So the light blue, that's the total precipitation each year over whole of Scandinavia. And the dark blue, that's the AR-related precipitation. And here you see it's a bit less because on that map, then that highlights where you have a lot of high fraction of AR precipitation, whereas this is sort of like an average, right? So in the map, some places we don't have much AR precipitation. So the fraction of a whole of Scandinavia, that's, yeah. Let's see here. Okay, then I have to calculate it, but it's basically maybe like 20% or so. If we don't only look at precipitation amounts, but also we thought maybe do we have stronger precipitation when we have ARs? Well, that seems to be the case. This is again the spatial average. It's a bit hard to see actually here. So I will look at the right one instead, focus on that. That's the maximum I had in my Scandinavian domain. And let's see, the blue one is when we have AR. The sort of red-orange one is when I don't have AR. And you can see the higher precipitation amounts, that's usually associated when we have ARs. Versus lower is when this is normalized, so the lower is when we don't have ARs. The shading here is all again from the different methods. So AR activity associated with higher precipitation rates, more extreme precipitation. Then we wonder how do those ARs move over Scandinavia, or also where they come from. So this was based on the K-means clustering. And here you spend a lot of time. Usually when you do K-means, people will ask you, okay, how do you find how many clusters you want? We spend quite a lot of time to try to quantify that objectively. So we use some silhouette scores and other methods I don't really understand too well. But he found that 4 was quite good. So you want the balance between not too many, because the more you increase, the better the fit will be. But you want to have a balance between fewer, but also being able to explain the variability. So we found that 4 seems to work well for all those methods. Actually, for some we need a bit more, but then some turn out to be similar. So then we merge them in the end. So here are the 4 first 2. First one, mostly over Denmark. That was where we had this maximum, if you remember, in all ARs. And then that's also mostly with precipitation over Denmark and southern Sweden. Next one, a bit less frequent, would be over sort of the northern coast of Norway. So those might not make it so much inland, but probably that's most of the precipitation falls then in these mountains. Then the third one that's the one that sort of crosses southern Sweden. And you might have noticed some in the animation that it's pathway. So that's quite relevant for both Gothenburg and also Uppsala, apparently here. But most of precipitation is still in Norway. That's some also over Sweden. And then last one, I call it a mixed bag. It's some over the more southern part of Norway, like along the west coast, and also interestingly some here in the Barents. That's one region I was very interested in when I studied Arctic, because the sea ice there, for example, has melted very fast, and it's quite easily affected by dynamics in the mid latitudes, but I think also affects dynamics here. Notice that the color range is different. So even if it looks quite a lot in the last one, it's a much lower percentages than the previous ones. So that one is a bit harder to define because it captures a bit different types. Okay, then just quickly look at the seasonality of those. So this is a lot of plots, but each row is one of those pathways. Each column is just a season. And what you should be able to see is that the colors sort of light up in the last column here. That's for autumn. So for most of these pathways, autumn is when they are most active. Actually, for the last one, that was not really the case. That's then it's more in the summer, then you have quite a lot of ARs in the barren terraces, and this is something I would be interested in looking a bit more into here. So I suspect maybe that could be also related to some sea ice dynamics, etc. But that's not something we have looked at yet. Then finally, we asked, okay, those pathways, are they affected by things, for example, like the large-scale circulation? And here we looked at this circulation pattern called the North Atlantic Oscillation, NAO. Familiar with. It's the dominant circulation teleconnection pattern, and especially in winter. And just a quick summary. When you have a positive phase, you have strong westerlies. The jet stream tends to be more like straight, so to say. So in winter, it's associated with warm and wet winters of Scandinavia. Versus if you have negative phase, then you can get this more meandering, wavy jet stream, weaker westerlies. So it's easier to get cold and dry Arctic air over Scandinavia. And so you would expect maybe more atmospheric rivers when you have positive phase. So we plot again all of them for different phases. So again, rows, different pathways and columns from negative to left to more positive to right. And general pattern here seems to be that we have more AR activity when you have more positive phase of the NAO. But some don't really show that as clearly, like the first pathway, for example. You notice that when the NAO is negative here, that's also, then the value increases also. Not so much, so we don't know if it could be just some randomness involved here. But quite interesting that this one is not as clearly when it comes to the negative parts. When it comes to positive parts, that's seen quite linearly related. So that actually brings me to my conclusions. So remember the questions we asked in the beginning. So now you can actually answer them. So how frequently do they occur? Well, if you think anywhere in Scandinavia, about 25% in an average year. But for specific regions then the maximum would be about 6% or roughly 22 AR days. But in general, less than that in most regions. But even though they are relatively infrequent, we see that they are associated with quite a large part of the total precipitation in some regions, especially in the mountains in Norway. So up to 41% of the total annual precipitation are associated with ARs for some regions, not all. How do they move? Well, we found that there were typically 4 AR patterns of Scandinavia. So one around Denmark, one along the northern west coast of Norway, one that sort of crosses Sweden, and then this kind of mixed bag of different ARs. And finally, we saw that ARs in general are more frequent in autumn and also when we have a strong positive phase of the North Atlantic Oscillation. With that, thank you for your attention. I'm happy to take your questions.
Yeah, thanks, Hans. So are there any questions from Zoom or from the room? For those of you on Zoom, you can either type them in the chat or unmute and ask them. or anyone in the room?
Thank you for the presentation. It was super interesting. I've actually been working quite closely on one paper with the PhD student that was working on atmospheric rivers here. So like trying to understand how well different machine learning, like large scale deep learning methods can track basically.
Yeah, I saw that paper.
Yeah.